So let's start now. Welcome to the third lecture of HDX. And today we'll look at a construction of HDX. Which is by Kaufman and Oppenheim. So Izhar is in the audience, so please direct all your questions to him. Okay, so just a quick recap of what local spectral, what we saw so far. So we saw that HDX are these simplicial complexes where in each level we have a set of subsets of the universe N. And local spectral expansion is just that at any level when you take a face and you look at the base graph with respect to this link, this base graph is a good expander. And this should hold for all links in the complex. And something that we saw is the trickle-down theorem, which says that once your top-level links are good expanders, then you get this HDX condition for all the links in the complex. And something that I mentioned at the very end of the talk last time was that if you look at any two levels in this complex, two levels that are really far apart, and if you look at the bipartite inclusion graph between them, where you connect two faces, if this face is contained in the top face, these graphs are good bipartite expanders. It can also be thought of as random walk mixing between these two levels. And something we discussed in the first lecture is that random hypergraphs, we do not have any good random model or any random model for constructing HDX. Yeah.
Was there if the random walks at every level converge, then
I think that's not true.
it's not true.
Yeah, because this is only for, so one thing you get from HDX is that even if you look at a link, the random walks, the same property would hold inside the links. And in fact, I think there are constructions where there's one combinatorial construction where the random walks mix, but it's not a local link spectral.
So the diff is that if the random walks in each link, if each random walk in each link converges, that.
Yes. Okay, good questions. So one thing that we saw in the first lecture was that we do not have a good random model for generating these high-dimensional expanders. So we mentioned one construction which looks at, which we get by quotienting some infinite graph. And that's quite a complicated construction by Lobotsky, Samuels, and Vishne. But today we'll be looking at this amazingly nice and simple construction by Kaufman and Oppenheim based on a different idea of taking cosets of groups. And today we'll only be looking at the 2D, two-dimensional construction. At the end of the talk, I will mention how to generalize this to higher dimensions.
Should x1 be x0?
Oh, yeah, sorry. Yeah. Okay, so again, what we want to do here is to construct vertices, edges, and triangles such that all vertex links so all vertex links are just graphs, and all these graphs are good expanders. And then, we will also show that the base graph is connected. And by the trickle-down theorem, you will immediately get that the whole complex is a good HDX. So let me define this general idea of coset complexes. And then we will instantiate it using the Kaufman and Oppenheim construction. Okay, just a quick recap. Given a group G and a subgroup H inside G, we will look at the left coset left cosets of H inside G, which will be sets of the following form. And we will also look at, like given a set of generators inside G, this will denote the subgroup generated by these generators. Okay, and so what is a coset complex? So for a coset complex in dimension D, or let's say just in dimension 2, we let G be any group, and we let and we take three subgroups of G, and then we let the vertices of our complex be the set of cosets of each Ki with respect to G. So the vertices of type 1 will be all cosets of K1 inside G. Yeah, and type I. So there will be three sets of vertices. So we will build a three-partite complex. And there will be no edges between any two vertices in the same type. But we will put in an edge between vertices in different types. So there will be an edge of type ij. This will be the set of edges G, Ki, G prime Kj, such that the intersection is non-empty. So you just take, you put in an edge between two cosets if they intersect in some element of G. And similarly, for triangles, all triangles will have all three types. So there's only one type of a triangle. So you'll put in a triangle again when the intersection of the cosets is non-empty. Yes.
Triple edge just says that every two intersect, and this says that all three intersect.
Yes, so it's actually a good exercise to check that every edge is actually contained in some triangle on top.
This property is, if is a triangle in the graph always a triangle in the sense of this? It depends on the groups. Like for all the groups that we look at, this is true. Like if you just have three edges, and then you ask, if three cosets all intersect pairwise, do they intersect mutually? all the groups that we look at.
Yeah, but okay. Yeah, so it's true for all the groups. I thought it's also true always. Is it?
No, but I guess what you said is not right. That's true. Always. Like that every edge is coming from a triangle, but no. Every edge.
What I meant was every edge here does come from some triangle. Like you can complete it to a triangle.
Yeah,
That is true.
sure, but it's a different question. It's a
Oh.
different
It's like, is it a clique complex?
Yeah, yeah. Okay, any more questions? In general, you have a face between a bunch of cosets when their intersection is non-empty. Yeah.
Maybe one thing is it's like, maybe we're saying that like if the cosets intersect, then there's some element like G.
Yeah, I'm going to.
Okay, sorry, yeah,
yeah, I'm
that's
going to
good.
write that out. Like this is one way you can define it. I'm going to write down some properties of this complex. Any more questions? So let me just do a quick, simple example. So let G be FQ to the 3, and let the cosets, let the subgroups Kx equal 0, y, z, such that so the first coset is just the yz plane, and similarly you have ky and kz. This will be the xy plane, and this is the xz plane. And now what is the coset complex of these guys with respect to G? So that's just going to be a very simple complex. The vertices are going to be, so the type X vertices are going to be just the YZ, like affine planes. So where you have the first coordinate to be fixed to some constant, and then you vary y and z. And similarly here you have the second coordinate to be fixed to some a prime, and you vary x, z, and so on. And now let's see when you have, now if you take any 3 guys, this is like saying we want to check if there's a triangle, and there will always be a triangle containing all 3 points, because these 3 planes will always intersect in at least one point. So you'll get a triangle for every 3 points. So this will be the so the set of triangles is just going to be all triples. And so you'll get the complete. So this complex is the complete 3-partite complex. So any questions about the example? Okay, so again, this is a dense complex because here you have all possible triangles. So what we want is to build a sparse complex where you have only, if you have n vertices, you have theta of n triangles. So the main idea is to instantiate the group and the subgroups in a way such that it's sparse. Okay. So let's just look at quick basic properties of these cosec complexes. Yeah?
Is it always expanding, and so is sparsity the only challenge?
Oh, sorry, you also need to prove expansion. Yeah. So the challenge is to get sparse and expanding. Okay, so as Noah pointed out, one way to think of a face is to just observe that every face or triangle is of the form G. Okay, let me just say triangle. And similarly, every edge between K1, like cosets 1 and 2, is going to be of the form GK1, GK2. So what's the proof of this? So this is just because if G1, K1 is intersect G2, K2 is non-empty, it's equal to some element G. And so you can oh, yeah. Wait. G belongs to this, and sorry. So then you can, so G prime. And so you can have a common element multiplying all the cosets. Okay. And this is one way to look at a triangle, but there might be 2 ways to label the same triangle. So we want to see that how many distinct triangles you have in the graph. So 2 triangles labeled by G and G prime are equal if G inverse G prime belongs to K1 intersect K2 intersect K3. So this is just because the first coset is equal to the second coset, implies that G prime inverse G belongs to K1. So this immediately gives us a count on the total number of triangles we would have. And that's going to be, so you have one triangle, you identify all the triangles each element in the intersection gives you, all elements in the intersection give you one triangle. And so the number of triangles you get is the number of cosets of the intersection with respect to G. So that's just going to be G divided by the Ki. Oh, maybe I'll draw a line here. Okay, and similarly, number of vertices of type I is just the number of cosets, so that's simply G by the size of Ki. And number of edges of type Ij is going to be G divided by Ki intersect Kj. Okay, and one one interesting symmetry that the complex has is that left multiplication by G by any element of G just is an automorphism for of the complex. So what this means is that if you multiply every face by G, if you had an edge in the original complex, after multiplication you will still have an edge. And similarly, if you had a triangle, you will still have a triangle. So this in particular implies that all links of type, all vertex links of type I are isomorphic to each other. So the link of the element K1 is going to be equal to the link of any coset of K1. So we are just going to, in our analysis, it suffices to analyze some one particular K1 link. Okay. And one interesting property that we will use is that the base graph or the one skeleton of G is connected if and only if the KIs generate G. So let me just show you one direction of this as by an example. So what we want to show is that if the KIs generate G, then you can find a path from any vertex in this complex to any other vertex. So let's say that you want to find a path from K1 to G of K2, or yeah. So these are two vertices, and since G is generated by these groups, you can write G as let's say G is equal to K1, K2, K3, where each Ki belongs to the group capital Ki. Then the path you get is just K1 is connected to little k1 times K2. So why is this? This is just because this element K1 is in both the is in K1. Okay, maybe I should call this something else. Okay, so K1 is connected to H1, K2. This is because H1 belongs to K1, and it also belongs to H1, K2 because K2 contains the identity element. And this way we can keep replacing, like adding one more thing from this. So H1, K2 is connected to H1, H2, K3, which is connected to GK2 by the same argument. Okay, so I'll leave the actual proof as an exercise. Okay, and finally, something that we'll use is the structure of the vertex links. And the nice property of these coset complexes is that the vertex link itself is a coset complex. So it's some kind of very nice recursive property. So the claim is that the link of K1 is just the complex K1, you take the group being K1, and you take cosets of it with respect to K1 intersect K2 and K1 intersect K3. And because all links are isomorphic, it suffices to just consider link of K1, link of K2, and link of K3. Okay, I'll just give a quick reason why this is true.
One level lower?
Yeah, this is going to be two groups because it's a link. Okay, so let's just look at the vertex K1 and see what are its neighbors in the complex. So its neighbors are going to be edges. So let's look at what are the edges that touch it. So edges touching it will be of the form K1, G, K2. Or, yeah. Sorry. Looked confused. So edges touching it have to have their first index to be K1. So G needs to belong to K1. And G also needs to belong to, if G belongs to, again by the same argument, if G belongs to K2, you will get back the same edge. So you will get a distinct edge whenever G belongs to K1 but not to K2. So the number of edges touching K1 is going to be the number of cosets of K1 intersect K2 inside K1. The same argument that we did here. So you'll get a different edge whenever you have a different coset.
The number of edges of type 1, 2.
Right, yeah.
Touching K.
Yeah. So in particular, the edges can be labeled by the cosets of K1 intersect K2 inside K1. And then you can, similarly, you get edges of type 1, 3, and you can also check that the triangles or the edges between these guys are going to be exactly the triangles in the original coset complex. So again, I'll leave this as an exercise. Okay, so any questions about these properties?
So this question of connectedness for the original complex, it doesn't like if you know it's connected and has that property, that doesn't imply that the links will be connected also, right? It's a separate condition that these intersections generate K1.
Sorry, are you asking about this
Yeah,
one?
I'm wondering if, I'm assuming that 4 for the base graph of the whole complex does not imply that the links are connected also.
Yeah, for the links to be connecting, you'll again need that these
two
generate
K1.
K1. Yeah.
No, but it follows from that. No,
It
so
does.
G is generated by K1, Q1, K2, K3. So for the link of K1 to be a link, K1 should be generated by K1 intersection K2 and intersection K3. Won't that? Oh,
No, it doesn't.
Yeah.
sorry. I'm wrong.
It doesn't, probably doesn't follow, but we'll show that they are expanders.
Yeah, sorry.
Sure, of course, yeah, I was
No,
confused
no,
about this
I'm wrong.
question, exactly, right, yeah.
Yeah.
I was wondering if, for some other reason, it happened. Okay.
Okay. So any more questions?
Do we need to assume the subgroups are normal or anything like that?
Yeah, there's no other assumptions, just, yeah, this is it.
It's probably bad.
Okay, so the main idea here is to actually choose the KIs to be very small. So each KI will just be a constant sized subgroup, but they're chosen so that they still generate a really large group. So let's see, when the KIs are small and the link can be just the size of KI. So the maximum number of triangles you can have is just going to be some constant times the number of vertices. But together they generate a group whose size you can vary the size to be as large as you want. So firstly, the group is chosen to be SL3. So 3 is because we have a two-dimensional complex, RM. So let me remind, firstly, SL3 R is the set of matrices with entries in the ring R with determinant 1. And Rm is chosen to be a polynomial ring, so over some finite field Fq. So okay, so what this means is each element of Rm is a degree m-1 polynomial in T. And you replace T to the m with 0. So like a m plus, for example, if you had the polynomial T to the m plus 1, that's replaced with 0. That's how you multiply and add stuff. Okay. Okay, so you can see that the group so with m, the group grows. So the size of the group is going to be roughly like q to the m, or at least q to the m. And the interesting part is to choose the subgroups. So K1 is chosen to be the subgroups generated by these upper triangular matrices, where you have a linear polynomial in these two entries. And actually, you can multiply these and check that this this is a group where you'll get a quadratic polynomial in this entry when you multiply these elements.
That's a Q, not a zero.
Oh, right, yeah. So this, so every entry, every element of K1 is going to be of this form. And it's determinant 1 just because it's upper triangular. And then K2 is going to be, again, upper triangular. Oh, sorry. Okay, so the way this is done is that you take these two represent basically, you're putting in linear polynomials in the entries 1, 2, and 2, 3. And here you're putting linear polynomials in 2, 3, and 3, 1. And finally, you'll put in linear polynomials in 3, 1, and 1, 2. Okay, so this might look magical, but when you look at the d-dimensional construction, like the way you do it is to take linear polynomials in the entries n, n plus 1.
Are we just doing like a cyclic?
Yeah, we are just doing a cyclic shift.
Shift on the coordinate, 3 coordinates?
Yes. Okay, any questions about this choice?
The coset complex is very natural. You can see why we'd go with it. Afterwards, I have no idea.
Okay, one thing I can see is that like these guys are finite, and then also their intersection is empty. Okay, so some quick properties of them are that their intersection is empty and they are finite and they generate all of G. So that's like an exercise. But, and yeah, so I don't know any more intuition beyond that.
G is growing,
Maybe.
right?
Yeah, so G is growing. These together generate G and their intersection is empty.
So we think of Q as fixed and M going.
Yeah, let me just write the parameters here. So we think of Q fixed. And also when we generalize to higher dimensions, we'll think of Q as like larger than D, but D will also be fixed. And then M goes to infinity. So our, we get the number of vertices of the complex go to infinity. Oh, and one nice thing that we will see is that the vertex links are very nice graphs. Yeah.
That makes things
There are, I think there are generalizations of the KO complex by O'Donnell, Pratt, and also by Inga and her co-authors. Okay, any more questions?
So why the cyclic shifts like in K3? I would have thought Popper would have L2, but it's if it was a cyclic shift.
Yeah, the cyclic shift is like modulo 3. So
Yeah, I see.
yeah, it becomes this. Oh, maybe I made a miss.
K3, shift L1 and L2.
I think it's correct, right?
If they, maybe it would be nice if the indices would be.
Oh.
But
L1 and L2.
Yeah, maybe this could be so. Or this is what you meant.
So I guess if their intersections are trivial, doesn't that mean the links are disconnected from what you said?
The overall intersection is trivial.
All three?
All three.
Ah, okay.
But not all
pairs.
two.
Okay.
Not
Sorry.
pairs.
Yes, okay.
Yeah. Yeah.
Well, maybe one thing that's worth saying in response to that question is that I guess in Linda's like papers about this, they consider instead of like L1 being linear and L2 also being linear, they consider L2 being constant and L1 being
Oh.
linear.
Okay.
And in that case, the links look almost like the spherical buildings that you
Okay.
talked about. But like they're the opposition. Or
They're,
whatever,
yeah,
but
they're
like-
subcomplex.
They're like dense subcomplexes in the sphere.
Right, really dense, like
Yeah.
close in total variation.
Yeah.
Yeah.
Like if you
Yeah,
go
so
on-
here the links are going to be very related to, so in the spherical buildings that we talked about, the links were lines versus plane graphs, which we know that their eigenvalue, second largest eigenvalue is 1 over square root q. Here, they won't really be lines versus planes, but we can still, they are very related to lines versus planes, and you still get 1 over square root q.
It's like somehow you give up on the dream of having exactly the line versus planes,
Yeah.
because that's very hard. And this is like much easier to describe, but not
Yeah.
quite as nice.
Okay, any more questions? Yeah.
Is there a reason why we identify some irreducible, like, if it's about is there some, is there intuition
I think
for
this already works, maybe.
You can do whatever. I mean,
Yeah.
maybe we should note for people who first day they I don't remember who talked about the mother group approach, where you start with a universal object and you take quotients. That's exactly what happens here. If you don't take this quotient, you have like an infinite group, and then you take this quotient, and you can take t to the n, and you can take irreducible polynomials, it doesn't matter. I mean, it all comes from the mother group, the infinite.
Okay, so let me just write down a quick, like, what are the quick sizes and number of triangles.
Mitali, do you mind if I
Yeah.
ask another question, I guess, related to the same thing? Is somehow, is the idea for why this is like the way to get a simpler construction? Was it previously one with like SL3Z and doing quotients, and then
No.
this is somehow simpler because it's a like function
No,
field
no, no.
instead of
There's no,
no?
SL3Z is harder. You don't get. But the reason was that we know expansion properties, property T. We know that for the mother group, and it's not written that way. But the reason to construct that is that the reason we know property T for the mother group is basically this link approach. So it was sort of the reason for property T was sort of buried in the literature coming from links. It wasn't really defined like that, but and that so it wasn't an unnatural step if you read the property T papers. That's what I'm saying.
Thanks.
Okay, thanks.
The mother group here is SL3FQT.
Yes.
Okay, thanks. So I'll write down some quick facts about the sizes. So firstly, the size of Ki is just q to the 7. You just have to choose 2 coefficients here, here, and 3 here. The size of G grows with m, and it roughly grows like q to the theta of m. And the intersection of Ki is empty. So the number of triangles is just equal to G. Oh. Oh, strip, sorry, yeah, it's 1. And finally, yeah, so the number of vertices is 3 times GM by q to the 7. Each vertex is contained in q to the 7 triangles. So it's a bounded degree HDX. We are thinking of q as constant. Okay, so now the interesting thing is to look at what the vertex links are and why are they expanding. Oh, also the KIs generate G. So the base graph is connected. So this is not not quite immediate, but it's possible to prove. I mean, if you think about it for some time. Okay, so let's look at the link of K1. So we know that this link is isomorphic to the coset complex of K1 with respect to the groups K1 intersect K2 and K1 intersect K3. So what should K1 intersect K2 be? Intuitively, here we do not, we just have, we have 0 here and 0 here. So together they have a linear polynomial only in this entry. So that's going to be the intersection. So this is going to be just the group 1, 1, 1, and L. And similarly, K1 intersect K3 will be the group 1, L, 0, 1, 1, 1. Okay, and now let me just write K1 here. So that is 1 L Q So the cosets of K1 intersect K2 inside K1, again, you can intuitively, you're actually just varying these guys. So the cosets are just going to be fix 0 here, because this is the same in both. So you just fix this to be 0 and vary L and Q. So these can be indexed by elements which have these guys as varying and everything else as the identity. And similarly, for K1 intersect K3, the cosets will be 1, 1, 1, L0, Q. Okay, so any questions about this? Okay, now we'll show that these two cosets are connected when these L and, okay, let's call this L prime and Q prime. When these L, Q, L prime, Q prime satisfy a certain condition. Let's call this matrix M2 and this matrix M3. So I can do this calculation, but I think I have very less time. But basically, I can just say how it comes about. So two cosets M2, LQ, they are going to be connected. So this is just a matrix. This matrix times the subgroup should have some intersection with the other coset. And then this just means that this M3 matrix inverse times M2 LQ, this should belong to K1 intersect K3 intersect or times K1 intersect K2 inverse. And you can see that any matrix from here times a matrix from here actually does not have any entry in its in the quadratic in this entry. Like the quadratic becomes 0. So when you work this out, you will get that they are connected only if this condition holds. So this is just some simple matrix multiplication. Okay, so what we get, so basically the intersection is non-empty, just means that this is equal to this guy for some elements, like some elements k belonging to k1, k2, k1 intersect k2, and k prime belonging to k1 intersect k3. And then you can check that multiplication of any two such things never has a quadratic in this entry. So when you multiply these two guys, the quadratic should cancel to 0. So that's what gives you this condition. This becomes one of, yeah, it's just a calculation. Okay, but this is really nice because this gives us a way to, gives us a really simple graph that we need to analyze. And this analysis was done in Harsha Saptarshi, which simplified the analysis of Kaufman and Oppenheim. So what we get is that this is the link of K1. It has vertices, which are cosets, but each coset is indexed by L, Q. We can kind of forget all the other information. And on the right-hand side, you have vertices indexed by L prime, Q prime. Here, L is a linear polynomial, Q is quadratic, and similarly here. And you have an edge exactly when L prime is equal to Q prime minus Q. So it's a really explicit graph on Q to the 5 vertices on each side, and each guy is connected to Q to the 4. It has Q to the 4 edges. Oh, sorry. And the way the spectral gap can be analyzed is to actually embed this graph into a slightly larger graph, which is on Q to the 6 elements. Where here you just have FQ cube cross FQ cube. Oh, yeah, sorry. Okay, so to analyze the spectrum of this graph, we can just embed it into a slightly larger graph. So each FQ cube can be thought of as polynomials polynomials with, or quadratic polynomials, so polynomials modulo some irreducible. So in some sense, each element here is just some quadratic polynomial Q1, comma Q2. So you can easily map each element here to some element here. And this will contain like all possible quadratic, comma quadratic, whereas this only contains linear, comma quadratic. And you can put in the same rule for an edge, like you want an edge to exist only when Q1 prime is equal to Q2 prime minus Q2. So an edge here, like, so you can see, you can check that this guy is actually an induced subgraph inside this larger graph. Yeah.
So I guess in the bottom graph, in general, there would be modular, there would be reduction modular,
yes,
irreducible polynomial, but above, since you never go above
yeah,
degree 2, there's no modular reduction.
Yes, exactly. So the top graph is exactly an induced subgraph, where you don't even need to reduce modulo the irreducible polynomial that is forming this field. And this is very similar. Okay, this is not really similar to lines versus planes, but you can analyze the eigenvalue of this graph very, like just using the same trick as the lines versus plane graph. So what you can do is to actually square this graph and look at the adjacency matrix you get. And that turns out to be a very nice matrix. It just turns out to be like some multiple of identity plus some tensor product. So you can easily get that you can also get all the eigenvalues of this graph. Let's call it H. So the eigenvalues, the second eigenvalue of H can be checked to be actually equal to 1 over square root Q cube. Yeah. Again, just the same analysis as the lines versus, same trick as that. And since this guy is an induced subgraph here, So firstly, note that the degree of each vertex here is going to be q cube. Yeah. Like you can choose any element here, and that gives you a unique element here. So the degree here is q cube, the degree here is q square. So this above graph is a induced subgraph of like slightly lower degree. So again, there's a simple fact that the graph here, let's call it the link. Lambda 2 of the link can be at most a factor of q more than this. Which is 1 over square root q. So that actually, modulo all these steps, that completes the analysis of the links. And each link here is like, firstly, we only need to check ki, and each ki is also quite symmetric. So that finishes the analysis. And then using the trickle-down theorem, you can get that the whole complex is a 1 over square root q local spectral expander. Okay, great. Thanks.
Questions?
So is the analysis in the empty link, like, is it tight? Is it is that correct?
I think it's open whether it's tight or whether whether it's a better spectral expander, right? No had mentioned to me. Okay, so the question is that whether the trickle-down theorem gives a tight analysis for the eigenvalue in the base graph.
No, it doesn't.
Yeah.
No, I don't know for this graph, but I know graphs in which we know the spectral gaps of both the one skeleton and of links, and it's like for Ramanujan, there is a paper like analyzing the two.
Yeah. I guess the question was for whether for this graph
For
is
this
it
graph,
tight.
I would guess it doesn't also, but that I
Okay.
don't know.
Thanks.
Maybe relatedly, I don't remember whether you said in one of the earlier ones, what is the kind of notion of like optimal local spectral expansion for an HDX? Like for a graph, we know an optimal relation between degree and an eigenvalue. Now there's another parameter, dimension as well.
Yeah, I think like we don't have any lower bound on the, like we don't have optimal lower bound, so all our constructions have degree q to the d square in the bottom graph while getting eigenvalue 1 over square root q in all the links. But we don't know whether this is tight.
You can get scaling exponential in dimension pretty trivially. As you sort of walk up, each time you meet some polynomial factor in lambda, possible vertices. So the open is between, is it exponential in d or exponential in d squared?
I see.
Yes.
Thanks.
Thank you, Mitali, again for this one.